Hello everyone, welcome to video 5.2, Heating Effect of Electric Currents. So as usual, this is the first slide I like to start off with, the data booklet references. There are a number of formulas in this section, so some which will be covered in this video, the rest which will be covered in the next video. So let me just swap over to my formula sheet here. Make sure that you have this in front of you throughout this lesson, throughout the homework, and throughout the examples, so that you're always able to reference this box here. Like I said, there are a lot of formulas in it. Remember that in SPH3U, we're doing 5.2. We're not doing 5.1. That's going to be covered in grade 12 physics. So just skip that part right there. Some of these formulas we're going to cover in this video, the rest in the next one. There is another page that's going to become useful for this video and for this section, and that is the page on electric circuit symbols. All right, so electric circuit symbols, you've got a lot of the symbols here. There are some symbols that have a slightly different picture, so they go by two different pictures. And there are some of these symbols that we're not going to use, and I'll talk about that when we get there. But for now, let's go back to the slides. So as the title suggests, heating effect of electric currents, we're looking at, well, when electricity or current flows through an electrical wire, why does it heat up, and what is that heating up called? And well, it's called resistance. If you've ever actually looked inside an electronic device and seen this little rod with a piece of ceramic in the middle with various colored stripes on it, oh, you've been looking at a resistor. And maybe it didn't look exactly like this. Maybe it had slightly different colors on it. We'll learn in a few slides what the color bands mean and how to read it. So here, for example, are two different versions of resistors. Now, these are what are known as fixed resistors, so fixed value resistors. So whatever amount of resistance they can provide, it's a constant. You cannot change it. Now, how is a resistor made? Well, you can see here in this diagram, you've got this piece of carbon. Now, carbon is what we call a semiconductor. And as its name suggests, it has properties of both a conductor and of an insulator. Okay, so conductors allow the easy flow of electrons through the material, and insulators fully prevent that flow of electrons. Excuse me. Now, some conductors are better than others, which we'll also explore later in the slides in this video. And there are some materials that have nice properties of both. Now, semiconductors are really useful for building things like computers because of their unique properties, which we're not going to get into in this video. So the idea is that carbon does conduct electricity, and carbon is what's inside of your pencil. Okay, so it's not actually lead. The pieces inside your pencil used to be made out of lead until it was discovered that it is in fact toxic, and it was replaced with graphite, and graphite is just sheets of carbon atoms. All right, so imagine you have a road. Okay, you've got a road here on the right, you're driving in your car, and you have to cross over this area and end up here on the road on the left. Well, the fastest way to do it would be to go exactly straight through. So if I have a solid piece of carbon here and the electrons are trying to pass through from one side to the other, they will just want to move in a straight line, right? Everything in nature wants the fastest, simplest way to do things. It wants to reach equilibrium the quickest way possible. So they would just travel straight, which wouldn't really help us very much. The whole point of a resistor is to, well, as its name suggests, increase resistance. So resist the flow of electrons, slow down the flow of electrons. By the way, electrons flow extremely fast through electrical wires. So you don't want them traveling too fast, or your wire's going to heat up a lot and could potentially melt and start a fire depending on where it is. So resistors are made to slow them down. But how do you slow them down? Well, if I was driving in a car and I wanted to slow someone down from starting at point A and reaching point B here on the left, I would have them drive through a longer distance. So if you notice here on the top, there's a little point that says carbon film spiraled away to give value. And so what happens is these spirals are cut inside of the carbon. So instead of the car being able to go straight now, it can only travel along the black road, the carbon road. So it has to spiral around and around and around this resistor until it finally gets through the end. So within the short amount of distance, or the short amount of resistor rather, it has to travel a very long distance, the electron, or if you're thinking of the car example, this would be the car. And depending on how many spirals there are, you can increase or decrease the resistance to whatever value you desire. Now, there are different kinds of resistors. On the previous slide, you saw something called a fixed resistor. So let me just pop back there for a second. So whatever resistance value this has, it will always be the same. You cannot increase it and you cannot decrease it. If you want a different resistance for a fixed resistor, you would have to build a new type of resistor. However, there are variable resistors. Okay? And these ones can work with wires being wound around the main core of the resistor. So how does it work? Okay, so you've got a metal lead here, and of course you've got these metal leads on the side here. So effectively you've got 3 leads. Okay, sometimes these variable resistors are called potentiometers. We're not going to get into a lot of detail about what the difference is, but if you do want to get into those specifics, that is what you would study in a course like electrical engineering in the university level. So the idea is, imagine first this is not here, this 3rd lead. If we attached one wire to the left side of this metal and we attached another wire to the right side of this metal, the electricity would have to come in from one side. So let's assume it's the left. It would come in through one side. It would have to go around this piece, so around all these hundreds or thousands of coils. So this would be getting very hot, and it would exit on the right. But perhaps you want to use this variable resistor for something that requires a bit less resistance. All right, so if we want less resistance, we would have the electrons travel through less wire. All right, so what do? Oh, sorry, wrong direction. What do? We have this extra piece here, almost like a harness. Okay, so now this piece can move back and it can move forward. All right, so left and right. Now, if we move this thing to the left, and it can slide left and right, if we move it to the left, then essentially what happens is the electrons come in through the left. They go through a certain amount of electrical coil. So let's say this piece is now right here where my mouse is going up and down. Okay, so the electrons would stop flowing at this point and they would come up and through that new metal piece. They wouldn't travel through the extra resistance. Why would they do all that extra hard work to exit on the right when they would be able to easily exit from this piece of metal? Right, so and since this thing can be slid left and right to any point that you want, any resistance could be created from very low by sliding it all the way to the left to very high by sliding it all the way to the right. So that's a variable resistor. And there are so many other types of resistors. There's ones that are affected by temperature, right? So if temperature changes, the resistance changes. Those are called thermistors. And there are resistors that are affected by the amount of light shining on them. These are called light-dependent resistors, or LDRs. All right, so by definition, electrical resistance, which we symbolize as capital R, is a measure of how difficult it is for the electrons to flow through the material, or said another way, for the current to flow through the material. Now, the unit for resistance is ohms. Okay, you can see here there is a symbol. This is the Greek letter omega. It is the capital omega. Okay, so we measure resistance using something called an ohm meter. In previous videos, you would have seen that current is measured using something called an ammeter, and voltage is measured using a voltmeter. A resistance is measured using an ohm meter. Right? So the prefix or the beginning of this word before meter is always the name of the unit. Now this device down here on the left, this is what's called a multimeter. So this is a nice digital device that can measure all 3 of those quantities depending on where you set the dial. So on this one, I've got voltage measurements on the top left, current measurements on the top right, and resistance on the bottom. But you'll notice that there are different settings. I mean, there's 200, 2000, 20K, 200K, 2000K. So all that means is whatever range your resistance is expected to be, you would put the dial on that spot. So for instance, if the resistance is expected to be in the 300s, you would put it on this first dial right here. If the resistance is expected to be in the thousands, you would put it on this next dial. In the tens of thousands, the next dial, etc. Okay, so let's say we want to measure the resistance across this resistor. Now, with a multimeter, you don't have to have a power source to measure the resistance. Now, if you're looking at that saying, well, why is that the case? In order to find the resistance, I have to see how hard it is for the current to flow through. And without a battery, current is not going to flow through it. Well, the way the multimeter is designed is such that you are not supposed to connect a voltage source to the resistor in order to figure out its resistance. The multimeter itself sends a tiny little current through, and by doing so, it measures what the resistance is. Okay. A couple things. If you ever see 0 with a decimal, an L, on the multimeter, it means the ohm meter is overloaded. Okay, the resistance is too high to be recorded. So for instance, if you're set in the 200 mode, you might have to increase it to the 2000 mode or 20,000 mode, etc. So in this case, it turns out that when you actually connect the leads, you end up with the resistance in the hundreds, 330.4 ohms. All right, now the various symbols. All right, so this right here, an empty rectangle with 2 leads on the ends, that's the fixed value resistor. Yeah, that's the one with the ceramic and the various color bands. It has 2 leads. We've got the variable resistor, and it's represented with an arrow going diagonally through the resistor box. This also has 2 leads. And we've got the potentiometer. This has 3 leads, and it's also a type of variable resistor. Now, I want to just quickly jump to the formula sheet here. We're going to see some more of these symbols in a second, but I want to show you one thing first. Resistor is down here, so you can see the symbol. You've got that empty rectangular box. There's another symbol for resistor that is widely used, and so I want you to become familiar with it as well. And it looks like this. Okay, so essentially you've got your 2 leads, one on the left and one on the right, and you've got a series of zigzag lines. You can put, 3 or 4 in between. And what this is meant to represent is inside the resistor, instead of traveling through a straight line, the electrons travel through a complex zigzag or spiraled pattern as they move through this distance. All right, so either one of these symbols can be used to represent a resistor. Just like the term weight and force of gravity both mean the same thing, both of these symbols mean the same thing. All right, let's go back to the slides. Okay, the symbol for a thermistor, right? The temperature resistant resistor, and the LDR. Now, with the thermistor, the resistance decreases when the temperature increases, and with the light dependent resistor, resistance decreases when the brightness increases. So those will have various applications. Now, how do we actually, well, what's another way to define resistance? Well, this specific definition of resistance is based on the formula, the ratio of the potential difference V across the material to the current I flowing through the material. All right, now some of you are looking at this and saying, what is potential difference V? Well, V is voltage. If you've ever looked at a battery, you would probably see that it has some kind of a rating on it. It might be 1.5 V, which is volts. It might be 4.5 volts. It might be 9 volts. But that is what's called the potential difference. So this is the ability for the electrons to actually be pushed through the circuit. But current, on the other hand, that is the flow of electrons. So if electrons are flowing very fast through the circuit, that means we have a high current. And if they're traveling very slowly, which would be the case if we had a high resistance, then we would have a low current. But anyways, we will come back to this formula again, R equals V over I. You have seen this formula before, not in this course, but it's first introduced in grade 9 science when you study the physics unit. Okay, all about electricity. In fact, a lot of the stuff covered in this video is just a repeat of grade 9 science. All right. Now the units for resistance, if you look based on this formula, it's going to be volts divided by the unit for current, which is amperes. Let me actually write this down on the paper so you see where all these units are coming from. So if we have R is equal to V over I, so voltage, and this is another word for potential difference. Voltage is the same thing as potential difference. So there's a lot of words that mean the same thing. Okay, so voltage is potential difference. This I is current. Current is measured in amperes, so capital A. And if you remember, that's actually one of the 7 base SI units. So that's ampere. Potential difference is measured in volts. Okay, so voltage is measured in volts, but another word is potential difference. And resistance and it always has to be capital R. Lowercase r is going to represent something else, as we'll see in the next video. Resistance is measured in ohms, and there's that Greek letter omega. In fact, this is capital omega. Lowercase omega stands for something else. All right. And we say that's ohms. All right. Let's go back. All right. A fixed resistor has a current of 18.2 milliamperes when it has 6 volts potential difference across it. What is its resistance? So hopefully you have the slides in front of you. So even when I switch screens like this, you still have the question in front of you. All right. So the current going through is 18.2 milliamperes. The prefix milli means times 10 to the minus 3, so I convert that right away. All right, and we know this is the current when a potential difference of 6 volts is applied across it. What is the resistance? Well, I know the expression for this. Resistance is equal to voltage divided by current. Volts is the SI unit for voltage, and amperes is the SI unit for current. So everything is good to go. That means my answer will be in volts per ampere, also known as ohms. All right, so let me grab my calculator. 6 divided by 18 times 10 to the minus 3. Oh, sorry, 18.2 times 10 to the minus 3. Okay, so 329.67 ohms. All right, I'm going to call that 330 ohms. Okay, we're going to work only with whole numbers for this question. Okay, so going back. Now, in the bottom right here, you've actually got a picture of this particular resistor. Okay, so there's the solution. Now, here is what that color coding actually means. Okay, so the orange band, so reading from one side to the other, the orange band starts and it's rated as a 3. So you have 2 oranges, so you have a 3 followed by a 3, and the brown means 1. So here's the resistor color code on the top right. So again, orange is 3. You have 2 of those, so 3, 3, and then a 1. But some of you might be looking at that and saying, well, we just found the resistance to be 330, so shouldn't the last band be black? Why is it brown? And the reason for that is because the last color tells you the number of zeros. So that means I have a 3 and a 3 followed by 1 0, which is 330. And this works for any kind of resistor. If you use this color code, you can figure out the resistance of any resistor. Okay, now let's understand what factors affect resistance of a material. And so to do that, we're going to consider 2 identical milkshakes. And inside those milkshakes are going to be straws. Now, in the first scenario, notice that the straws have the same diameter, but they have different lengths. Okay, so if you had a choice, I mean, obviously, you probably wouldn't want to get a straw that starts right where the milkshake starts. But in reality, would you like a regular size straw or a straw that is twice as tall as the cup? Which would be easier for you to drink out of? Okay, now, or which would allow you to suck the milkshake up through the straw more easily? Okay, the shorter straw will allow you to suck the milkshake through more easily because it has to travel through less distance. And so what we find is that the longer the straw or the longer the wire, the more resistance there's going to be. So resistance is proportional to length. Now, what does proportional mean? When we say that 2 things are proportional, that means as one increases, the other increases. If one decreases, the other decreases. And I'm going to show you specifically how that's going to happen in just a moment. Okay, the second variable we're going to investigate while holding everything else constant is the diameter of the straw. Would you rather drink the milkshake out of the really thin, tiny straw or the standard diameter straw? Well, most of you would probably say the standard diameter straw, because this one, you would have to suck through it very hard in order to get any sort of amount of milkshake out. Okay, so what we find is that the diameter, which can also be represented with the cross-section area, okay, so the smaller the cross-sectional area, the more resistance there is. That means that resistance is proportional to the reciprocal of area. So what that means is if area gets bigger, right? So if the denominator on the right here gets bigger, 1 divided by a big number becomes a small number, right? So that means resistance would be smaller. Now, I just used a term called cross-section area. I'm going to explain to you what that means. Cross-section area, it just really means this. If I have some sort of three-dimensional object, so let's say I have a box of tissues, okay, and I want to cut this, okay, so I take a knife and I slice it. If I slice it perpendicular to the top surface, what shape am I going to get out, right? So if I cut it, what shape am I going to see on the end? Well, I'm going to see a rectangle. That's the cross-sectional area. So if you cut it, so if you cut the shape and you look at the end, what shape are you going to see? The cross-sectional area of this marker lid is a circle. Okay, so if I have a cylinder, what's the cross-sectional area? Well, if I look at the end, I'm going to see a circle. Likewise, if I slice this, what am I going to see? I'm going to see a circle on the end. So that's what it means to have a cross-section. And a cross-section area just means you calculate the area of this side or this side, whatever shape happens to be on the end. So let me just label that cross-section or cross-sectional area. All right. Now, I did also tell you that I was going to explain in more detail what it means for two things to be proportional to each other. You're going to see this again in mathematics, but it's very important that you understand how this works now. Okay. So this is a bit of a math lesson for you all. Proportionality. Okay. Let's say we have two variables, okay? Usually we call them x and y. X is the independent variable, y is the dependent. X is the input, y is the output. So you can choose x and y, or you can choose any other letters like a and b. So let's say a and b are proportional to each other. That means they have the same tendency. If one increases, the other has to increase. If one decreases, the other has to decrease. You cannot have two things that are proportional and have one thing increase while the other decreases. It doesn't work. Okay, so if you're ever given a proportionality statement, and this is the proportionality symbol, okay, it kind of looks like a little fish, kind of looks like an alpha symbol too, okay? If A is proportional to B, how do we turn this into an equation? If A is proportional to B, then A is equal to B times a constant. This is always, always, always true. If you remember this, it will make your life so much easier. If two variables are proportional to each other, then one is equal to the other times a constant. Now, I didn't have to put the constant on the right. I could stick it on the left. It doesn't matter. It just means that depending on which side it's on, that constant would just take a different value. Also, that constant is what we say is an element of the real numbers. Okay, so if you remember in mathematics, real numbers, so if you haven't actually been introduced to this yet, this will be your first time. So these are the real numbers. That's what the R stands for. To say that K, and this thing here means an element of, and again, all this you're going to learn in math, K is an element of the real numbers. Real numbers, this includes negative numbers, positive numbers, it includes decimals, it includes zero, it includes everything. Any number that you could possibly think of in your head is considered a real number. Okay, so why is that significant? Because that means this thing can be positive, negative, decimal, whole numbers, zero. It can be anything. Well, it wouldn't be zero because in that case you wouldn't have a scenario. So we'll just put a little disclaimer there: K does not equal zero. All right, now if A is proportional to B, A is equal to a constant times B. And that's true for any two variables. So now let's say if y is proportional to x, okay, then y is equal to a constant times x. Now that formula should look somewhat familiar to you. Now in grade 9, you learned the equation of a straight line. And that's essentially what you have here. You have your independent variable on one side, your dependent variable, independent on the right, dependent on the left. And we know that the relationship between them is the product of a constant. In grade 9, you would have seen that y is equal to mx plus b. this is a straight line with y-intercept b, slope m, and with the variables x and y. So if you compare this to the equation on top, what's the y-intercept? It's 0. What's the slope? Whatever that proportionality constant happens to be. So that k is the proportionality constant. Now, if you have a straight line with a y-intercept of 0, it's going to look something like this. So there's x, there's y, and there's your graph. Now, it doesn't have to be the line y is equal to x. It could look something like this. It could look something like this. It could be any sort of line, as long as it goes through y-intercept of 0, and as one variable increases, the other increases, or they both decrease together. Okay, that's what it means to be proportional. So when we say that resistance is proportional to length, and that resistance is proportional to the reciprocal of area, really what we're saying is that as length increases, resistance increases. As area increases, well, what happens? Resistance has to decrease, right? Because this is reciprocal proportionality. If you wanted to, sometimes this is also written as R is inversely proportional to A. So these two things mean the same thing. So just, be careful with that. Overall, we can make the expression R is proportional to L over A. Now, based on everything that I've explained to you, if R is proportional to L over A, then R has to equal a constant times L over A. So our job is to figure out what that constant is and what it represents. And that will be the topic of discussion over the next couple of slides. Now, trying to figure out that constant comes down to understanding why we use different materials in electrical work. After all, we saw that carbon does conduct electricity, but we don't use carbon quite a lot, especially not in wires. Wires are usually made up of copper. Why is it made out of copper, and why not another material? Well, it all has to do with not just its resistance, but that constant of proportionality, which we're going to call the resistivity. Now, that word is going to be on the next slide, but in the meantime, you have the symbol here. This is the Greek letter rho, and I will write that down on this sheet. Let me just move that. Okay. So resistivity is given by this letter right here. This is the Greek letter rho. Now, again, some of you are looking at this and saying, I remember that symbol, and it represented density, which is mass divided by volume, and it still does. But it's also going to represent resistivity now. There are so many variables and just variables in physics that a lot of the letters had to be used up twice. Okay. So this is our constant of proportionality. So instead of R equals KL over A, we have rho L over A. So rho is our constant of proportionality. And if we want to rearrange for rho, it's RA divided by L. Each material has a different resistivity. Now, this table tells us the resistivities in something called the temperature coefficient for various materials at 20 degrees Celsius. Generally speaking, the reference values for the resistivity is always given at 20 Celsius. And the reason for that, which we're not going to get into a whole lot, is because temperature affects resistance. Now, if you had to guess, if your computer was very hot, okay, so if you touched the AC adapter on your laptop or your desktop computer, well, actually, it wouldn't be a desktop. If you touched the AC adapter on your laptop computer and it was very hot, do you think your computer would be running slower or faster? And the answer is, well, it would probably be running slower because you've had it on a long time. It's been running a lot. If you want resistance to decrease, you have to keep the temperature of the electrical device down. This is why a lot of people who buy expensive servers, whether it's for gaming or business, they invest in very expensive, very high quality cooling systems. Those cooling systems inside of the servers can consist of fans. They can consist of pipes of water just running through the inside of the server just to cool it down. All right. In your car, you also have a cooling system. anything that is electrical requires a cooling system because the hotter it gets, the less it's going to work properly. So this thing right here, alpha, we're not going to be studying this. You're going to see it appear here and there. This thing is called the temperature coefficient. So that's all you need to really know. And that this thing tells us how the resistance is affected by temperature. We're not going to be using these numbers in any calculation, but if you do study this further, this will come up. Here is rho, the resistivity, which we can see is measured in ohm meters. Now that is not abbreviated into anything simpler. We just say ohm meters. So here's the resistivity for our various conductors, and we've got semiconductors over here, and we've got non-conductors on the side here. Notice that the non-conductors, glass, rubber, wood, check out their resistivities. They are enormous. 10 to the 12, 10 to the 15, 10 to the 10. Those are very, very large numbers. But if you look at the resistivity of a conductor, it's on the order of 10 to the minus 8. Okay? So they're all on the order of 10 to the minus 8. With semiconductors, they vary, but you also have to remember that semiconductors have a lot of other special properties, which you will learn about in first-year university should you decide to study materials engineering. So these have a lot of interesting properties that allow them to work nicely in a computer. All right, I want to study this column here, the conductors column. So we've got aluminum, copper, iron, mercury, nichrome, nickel, platinum, silver, and tungsten. Tungsten, it's that filament that was used in incandescent bulbs. So not the spiral light bulbs, those would be the fluorescent ones. Incandescent would be the standard bulb. Okay, this is the filament that was inside, which would heat up when the electricity was passed through it and subsequently glow and produce light. Now, looking at this table, we can see that something that has a very high resistance, or two things that have very high resistance, is nichrome and mercury. Now, resistance and resistivity, they're proportional, so this is irrelevant of the diameter and the length of the material, so that's why these values are nice. Once you start talking about resistance, you're taking into account the diameter and the length. So it's a little bit more specific, but nonetheless, if we look at this table, things that have a very low or the lowest resistivity, the lowest resistivity seems to be attributed to silver and copper. Now, if you've ever opened up any kind of electrical device, so if you open up the back of your laptop to clean it or to grease various parts, if you've ever seen the inside of an electrical wire, they're made out of copper. Now, why would it be made out of copper when silver has a lower resistivity? If you answered that silver is more expensive, you're right. That's really what it comes down to. Silver is so much more expensive than copper, which is why our electrical wires running outside are not made out of silver. Copper is pretty expensive, but not nearly as much as silver. Now, some of you who are technology enthusiasts, if you like to buy the very best technology and accessories for your computer or your TV, you would know that if you've ever gone to buy a nice HDMI cable, the ends of the cable would be plated with gold. Now, it's not something fancy. It's not like a piece of jewelry that just hangs around your neck. Having gold on the end of the HDMI cable or having any sort of electrical device gold plated actually increases the conductivity. It decreases the resistance of the electrical component. Now, if you are to actually look up the resistivity of gold, you would find that it's actually higher than both silver and copper. It's higher than copper. In fact, silver is 1.59 times 10 to the minus 8. Copper is 1.70 times 10 to the minus 8. Gold is 2.40 times 10 to the minus 8. All right, it's much bigger. So then why would gold be a better suggestion? Why would gold be a better option to plate the ends of the HDMI cable? Or why are gold pieces in your computer so much more valuable? And it's not just about the price, it's about its ability to conduct. It clearly has a higher resistivity, so why is it preferable? I'm going to let you all think about that. Okay, it does say here, note the resistance depends on temperature. The IBO does not require us to explore this facet of resistivity. Whether you're IB or whether you're not IB, temperature increase means increase in resistance, and really that's as far as we're going to take it. And all the reference levels for resistivity and resistance are given at 20 degrees Celsius. Okay, Example, what is the resistance of a 0.00200 meter long carbon core resistor having a core diameter of, excuse me, excuse me, of 0.000100 meters? Okay, assume the temperature is 20 Celsius. The reason it's telling you this is because they're telling you it's a carbon core. And so the fact that I know that, I need to look up the resistivity. So I'm just going to pop back over here for a second. Resistivity of carbon, it's here under semiconductor. It's 3,600 times 10 to the minus 8 ohm meters. Okay, now before I forget that, I'm going to switch over here to my page and write that down. So the resistivity of carbon is 3,600 times 10 to the minus 8 ohm meters. Sometimes I put those little ticks on the end, sometimes I don't. It's really up to you. We are looking for resistance, and we are given the length of the carbon core resistor. So the length is 0.00200 meters. All these extra zeros just have to do with significant figures. Okay, so that's for the IB students to worry about. So this would be 1, 2, 3 significant figures. Let's see here. The diameter is 0.000100 meters. Okay, so we have to find the resistance. Now, we actually haven't flipped back to our formula booklet in a while, but just taking a look at this, there's the formula at the bottom here of box 5.2. Rho equals RA over L. So if you ever forget, there it is. And actually up here is R equals V over I. So we've already covered 2 of the formulas so far. So rho equals RA over L. Since we're looking for resistance, we're going to rearrange this formula for R. So that's rho L over A. In fact, you might actually just remember this one first, since that's how we derived it. Okay, now A is the cross-section area. Well, cross-section of what? It's the cross-section of the carbon core. Whether it's a carbon core or it's a wire, the shape is going to be a cylinder. And so if you cut that cylinder, what shape are you going to have when you look at the end? You're going to have a circle. Right? So the diameter of a circle, we know what that represents, but we care about the cross-sectional area. Now, if you remember your geometry formulas, the area of a circle is pi r squared. And so we're going to need to know that to calculate A. Right? Now, pi r squared, what is diameter? Diameter is r divided by 2. Diameter is twice the radius. So to take diameter and divide it by 2, we're going to get the radius. So dividing this number by 2, we're going to have 0.0000500 meters. Okay, so we just half that. All right, so we are going to now calculate R. So R is rho. Everything's in SI units, so we're good to go on that front. 3,600 times 10 to the minus 8 ohms, ohm meters. And L is 0.002. There's a lot of zeros here, so make sure you don't miss anything. 0.00200 meters. And, excuse me. And what do we have down here? Area is pi r squared, and r is right there, 0.0000500 meters. So now we can see the meters getting squared on the bottom. We'll cancel with these 2 meters on top, leaving me with ohms, which is exactly what I need. So 3,600 times 10 to the minus 8 times point, and again, watch very carefully. Don't mess up any zeros there. 0.002, okay, and then divide that by pi times 0.00005, close bracket, and square that, close bracket. Okay, 9.17. So resistance is 9.17 ohms. Okay, so there we go. Let's go back to the slides. All right, Ohm's law. Ohm's law you would have learned in grade 9 science in the physics unit. And we actually already saw Ohm's law, but we're going to see it using a slightly different look now. Instead of R equals V over I, as it is in your formula booklet, most people actually remember it as V equals I times R. So In the 1800s, German physicist George Ohm, he studied resistance, and he came to this conclusion. Provided the temperature is kept constant, the resistance of very many materials is constant over a wide range of applied potential differences, and therefore the potential difference is proportional to the current. Right, so if two things are proportional, right, so potential difference is proportional to the current, so V is proportional to I, that means V is equal to I times a constant. This is what we've been talking about this entire time with proportionalities. What's that constant? It's resistance, capital R. Okay, so that's how we go from left to right. All right. Now, Ohm's law, as you might imagine, it only applies to components and circuits that have a constant resistance value. Not all materials that provide a resistance have a constant resistance value. Sometimes as you increase the current, the resistance actually increases, which is not illogical. So we have different terms to describe these different types of materials. If a material has constant resistance while the current is increased or the voltage is increased, we call that material ohmic, okay, because it follows Ohm's law. So we're going to be looking at the following three cases. So we have three different graphs here, voltage versus current. We have to label these graphs with the following labels: ohmic, non-ohmic, R increasing, R decreasing, or R constant. Before we solve this on the slide, I want to actually do this on a sheet of paper. Okay, so we said that V is proportional to I. The potential difference or voltage is proportional to the current. So if V is proportional to I, then V is equal to a constant times I, except we just happen to find out that that constant is the resistance. So V is equal to R times I, or as it's usually just written, I times R. Doesn't matter, multiplication is commutative. So what that means is if I actually want to draw a graph, and we did this already, so hopefully this part is a review for you. Okay, so V on the y-axis and I on the x-axis. If two things are proportional, remember we are looking and comparing this to the equation. So compare this one to the equation y equals mx plus b. Well, the y-intercept is 0, right? So I have to start right here. What's my independent variable? It's I. What's my dependent variable? It's v. What's my slope? It's r. So however your slope is, so if I have a small slope, so something like this would be a small resistance, right? If I have a very steep slope, that would be a very large resistance. So small r, large R, and then the Goldilocks R would be something in the middle. Okay, so this is a middle R. Okay, middle R. But what we see is that it has to be a straight line because it follows the y equals mx plus b profile. Now, if we look at the three options we have, so let me just quickly sketch the three graphs from these slides. You don't have to do this. You don't have to do this part. You don't have to re-sketch it out on a piece of paper because you have the graphs in front of you on the piece of paper you printed. If not, then just write it in now. V, I, V, I, V, I. Okay, so one graph looks like this, one graph is straight, and one graph is curving like this. All right, so resistance is given by the slope of the V versus I graph. Okay, so what we're going to do is inspect something called the slope of the tangents. And what we're going to do is inspect how that slope changes from left to right. Okay, so if we start on the graph on the left, we look at the slopes of the tangents. Now, tangent just means, so slope of the tangent. Tangent just means a straight line attached to the curve at a single point, which is representative of the slope of the curve at that point. So for instance, if I looked at this point on the first curve, what's the slope there? Well, it looks something like this. The slope of the curve at that instance looks like that. If I pick a point over here, what does the slope look like there? It's a bit shallower. So the slope looks something like this. And if we move to the right, all the way up here, My slope is getting very steep at that point. So that's what my tangent looks like. But what I can see as I move from left to right is that my tangents are getting steeper and steeper. They're getting more and more positive. So I start off with a small positive and getting more positive and even more positive here. Right? My positive slopes are getting bigger and bigger. So what that means is here, the resistance is increasing. Okay. Now in this case, I have a constant slope throughout. So whether I pick this point or this point or this point, the slope of the tangent is always the same because, well, it's a straight line, right? If you draw a straight line to a straight line, of course, they're going to have the same slope. So this means we have a constant resistance. And finally, let's look at the graph on the right. If I pick 3 random points, okay, so the first one has a very positive slope. Okay, the next one here, the tangent looks something like this. Okay, so this one is positive, but it's getting a bit less positive. And finally over here, well, now we're getting pretty shallow, almost 0, but not quite. And so we have a very small positive slope. So in this particular case, my resistance values are decreasing. Okay, so increasing slope, increasing resistance. Constant slope, constant resistance. Decreasing slope, decreasing resistance. But resistance has to be positive. That's why in all 3 of these curves, the slopes, while they're changing, either constant, increasing, or decreasing, they're always positive, right? So you're not going to have negative resistance. If you had negative resistance, that would be some kind of material that magically makes your electrons flow even faster than they normally would. And I guarantee if you invent something like that, you're going to win the Nobel Prize in physics. Okay, so now that we've established that, remember that if a material is ohmic, that means it follows Ohm's law, and that means it has a constant resistance. That means that the only one of these that is ohmic is the one in the middle, because it's the only one that has a straight line relationship going through the origin. Okay, so these 2 on the right and left, these are non-ohmic because their resistance values are not constant. Okay, back to the slides. So everything I just did is right here on the slides. This slide here, as you can clearly see on the top right, this is not on your slides, but it's still important for you to understand the process with which I solve the question on the slide. Okay, so on this slide, we are told the IV, or the current voltage characteristic, is shown for a non-ohmic component. Okay, we can clearly see this is a non-ohmic component because it's a curve. It's not a straight line. Sketch in the IV characteristic for a 40 ohm ohmic component in the range of 0 to 6.0 volts. Okay, so you can do this with me. We're just going to quickly sketch this. So what I'm going to do is draw this Cartesian axis. So I've got voltage measured in volts on the horizontal axis, and I've got current measured in milliamperes, so pay really close attention to that. So I've got 150 at the top, and then about a third of the way down from that I've got 100, and about another third of the way down from that I've got 50, and there's 0 at the bottom. This thing goes to 8, so half of that is 4. There's 6, there's 2. All right, so let's see. Our original graph curves from 0 to 6 volts. Okay, so you know what? I'm not going to draw my original graph. But what I am told is that we have a 40 ohm ohmic component. That means the resistance is constant, right? As you would expect. We're clearly given the value here. So we want to draw in the characteristics. Now, you got to be a little careful here because if you remember what we were doing before, we were looking at voltage versus current, and we said when you plot voltage versus current, in other words, y versus x, the slope is resistance. But here I don't have voltage versus current. I have current versus voltage. It's not the same. So that means the slope is not resistance. So let me put a note here. Note, slope here does not equal r, since it's a graph of I versus V, not V versus I. So that's important. Okay, now let's try to find a relationship here. So just as before, we would have had V is equal to R times I, right? So Y equals mx. Here we have I as the independent variable. So we're going to have I is equal to, and if we rearrange this formula for I, what do we get? We get V divided by R. Now, before you look at that and say, that's not a straight line, well, it is actually, because your independent variable is here. So essentially what I have here is Y is equal to X over some number, okay? Okay, we'll just call it R. Or if you want, you can even call it 40 because it's 40. Y is equal to X over 40. If I have an expression like this, I can actually rewrite it as Y is equal to 1 over 40 times X. And now it looks like a straight line again, right? So we have Y equals mx plus V. And so what that means is it's the same idea here. I have I is equal to 1 over R times V. And so that's I is equal to 1 over 40 times V. If it helps you to see it like this, by all means, write it like that. But some of you will just be comfortable writing it like this and understanding that it's a straight line. Whatever you feel comfortable with is completely fine. Okay, so what we are asked to do is pretty much sketch in the graph that represents resistance on this graph of current versus voltage for the ohmic component at a resistance of 40 ohms. And now I understand that this is the relationship that connects the current with the voltage for that particular component. Now, I have to sketch this between 0 and 6 volts. So I'm just going to plot 2 points. Okay, so I know this is going to be a straight line. Whether you do V versus I or I versus V, we clearly showed it follows the Y equals mx plus B pattern. And to create a straight line, you only need 2 points. So my 2 points are going to be at V, the voltage is equal to 0 volts, and voltage is equal to 6 volts. Now, this is unfortunately one of the annoying things in physics, and that is that voltage, and so the unit for voltage, which is volts, and the symbol for voltage, they look exactly the same. It's capital V. So when you write it, I mean, some of you might want to write the V's a little different. If you look at the slide, you can see that they've italicized one V, right? So the variable and the unit is just left normal. Yeah, some books will bold one of them, but I mean, really, you don't need to do that. This is just one of the inconvenient things we get used to in physics. So, all right, so let's figure out what the Y values or the I values are for these points. Right, so if I plug in 0 for V, I get I is equal to, and let's just call this V1 and V2. So this is I1. So that's going to be V1 over 40. Okay, so that's 0 divided by 40. Okay, for those of you that know your mathematics, 0 divided by any number is 0. It doesn't matter what you divide it by as long as it's not 0. 0 divided by any non-zero number, I should say, is always 0. You cannot, however, divide a number that is not 0 by 0. Okay? All right, so I2 is equal to V2 over 40. So that's 6 over 40, which is, let's grab our calculator, 0.15. Okay, so 0.15 amps. Now, before you go looking for 0.15 on your scale, which would be all the way down here, you got to remember that this vertical scale is in milliamps. This value we just calculated is in amps, right? So you have a couple options. You can either convert the scale to amps, or you can convert your number down here to milliamps, right? So the conversion between the regular unit of any unit, so whether it's amps or grams, and the milliversion of it, to go from this to the milliversion, you have to increase the value by 1,000 times, right? So for instance, if I had 20 milliamps, I know that's 20 times 10 to the minus 3 amps. Excuse me. Right? To go from a small unit to a big unit, my number has to get smaller. But if I have 20 amps, how many milliamps would that be? Well, I'm going to a smaller unit, so the number has to get bigger. Okay, so that would become 20 times 10 to the 3 amps, or 20,000 amps. So milliamps. And so what's essentially happening is we're taking the decimal from the regular symbol and we're moving it to the right 3 spaces. So 0.15 would actually become 150, okay, milliamps, because that decimal would move 1, 2, 3 times, and that third spot gives a 0. Okay. Done another way, if that was a little bit confusing for you, you can just look at these values in milliamps and convert them to amps. So all of these would be times 10 to the minus 3, or looked at another way, you would take these decimals and move them to the left 3 spaces. So 1, 2, 3, and this would become 0.150 amps. Okay, this one would become 0.100 amps. This one would become 0.050 amps. Okay, so we want 0.15 amps, and that corresponds to 6 volts. So 6 volts, 0.15, so there's 1 point, and I found my other point, it's 0, 0. Okay, so at that point you could have actually anticipated from the start. And I'm just going to connect these 2 points with a straight line, and there it is. There's the IV characteristic for the 40 ohmic component from the range of 0 to 6 volts. Okay, back to the slides. In this video, this was the only part that you did not have on your slides, by the way. All right, here we go. The graph shows the applied voltage V versus resulting current through a tungsten filament lamp. So remember I said the filament lamp, or the tungsten filament lamp, this is your traditional light bulb that heats up a lot. It wastes 90% of the electricity that's provided to it by turning it into heat. Only 10% of that energy becomes light. So it's only 10% efficient. Okay, so we want to find the resistance when the current is 0.5 milliamps and 1.5 milliamps. And then we have to answer the question, is this filament ohmic or non-ohmic? Well, we can answer that question once we get the values for resistance, or we could answer that question simply looking at the graph. We have a graph of voltage versus current. That means the instantaneous slopes represent resistance, right? And you can clearly see the slopes from left to right are increasing. They're getting more and more positive. And so because the resistance is not constant, this material is not ohmic. It's non-ohmic. All right. In order to find the resistance, all we have to really use is Ohm's law, right? So let me switch screens for just a second, then we'll come back to the slides. Okay, so remember on the formula sheet, I have R equals V divided by I, right? It's the ratio of voltage to current at that particular point to figure out what the resistance is. So if I want to find the resistance at 0.5 milliamps, well, guess what? My horizontal axis is already in milliamps and my vertical axis is in volts. So at 0.5 milliamps, I can see that the Y value, well, let's take a look. For 1, 2, 3, 4, 5 boxes, I have 0.2. So imagine that was 20. 20 divided by 5 is 4. So 0.2 divided by 5 is 0.04. So each one of these boxes represents 0.04. So 2 of them would be 0.08 volts. All right, and I know the relationship R is equal to V divided by I. So what's my V is 0.08. My current, make sure you plug it in using SI units. 0.5 milliamps is 0.5 times 10 to the minus 3 amps. And sure enough, when you calculate that, you get 160 ohms. At 1.5 milliamps, we do the same thing, and we can see an easier value here. We have 0.6 volts, so R is equal to V divided by I. So 0.6 divided by 1.5 times 10 to the minus 3, that's 400 ohms. So even now, based on this conclusion, because the resistances are different at various current levels, this device is non-ohmic. But of course, you could have explained that using just the fact of the curve being present as well. Okay, explain why a lamp filament might be non-ohmic. This goes a little bit beyond the course, but it touches upon the course as well. So we're just going to go over it while we're here. Okay, so inside the bulb, we said that there's tungsten. That's what that little filament's made of. When the light bulb burns out, if you look really carefully inside of it, you will see that little filament kind of broken in the middle, almost as if someone's cut it. Okay, it breaks, and so the electricity can't flow because the circuit is no longer closed. Now the resistivity of that is, 5.6 times 10 to the minus 8. It's got its own particular temperature coefficient, which means that the higher the temperature, well, the more this thing's going to heat up and the more resistance there's going to be overall. Okay. All right. Power. So I mentioned before that we would get back to power eventually. We didn't cover it in earlier videos, earlier units. We are covering it now. There are some things on this slide which we are not covering, and I have crossed those things out. So if you see them on your slides, please cross them out. If they are crossed out on this slide and you don't have it on your slide, just don't even write it down, okay? Because it's stuff that will be covered in grade 12 physics. So even though it says recall, for you, it's just going to be, guess what? Power is the rate at which work is being done. Okay, so power is equal to work divided by time. So that's what the W stands for. It does not stand for weight. It stands for work. Okay, so let me just, let me go here for a second. So power is equal to work divided by time. What you got to remember is work, depending on the scenario, can also be set equal to the change in energy. So another convenient formula for power is actually delta E over delta T, okay, or T. All right, so just wanted to put that out there. All right, so you see all this stuff is crossed out because we are not doing 5.1 until grade 12 physics. But what I want you to understand is that this formula is going to also be quite helpful. In order to figure out the power dissipated by an electrical component or consumed by that electrical component, where you know its current and you know its potential difference or voltage, you can figure out what that power value is. P is equal to I times V, and that is in your formula booklet. Now, if you were actually to look at your formula booklet, you would see that there's two more formulas there next to it. Next to P is equal to I times V, or V times I. And they are P is equal to I squared times R and V squared divided by R. And really it just comes down to taking Ohm's law right here and plugging it in for, or substituting V in for V, or I in for I. Okay, and when you do that, you get these respective formulas. So you know what, we can do that from scratch here. Okay, so if I have P is equal to V times I, and I know that V is equal to I times R. If I plug V in for the V on the left, I'm going to get I times R times I. I times I is I squared, so there's I squared times R. Okay, so there's our first formula. All right, the second formula, P is equal to V times I. Now, if I rearrange Ohm's law for I get I is equal to V over R. Okay, so that's V times V over R, and I get V squared divided by R. So there's my other formula. So these three formulas are on your data booklet, right here. Okay, so depending on what the question gives you, whether it gives you voltage and current, or current and resistance, or voltage and resistance, you can use any one of those formulas. Okay, let's go back to the slides. Okay, so that's the formula for electrical power. All right, the graph shows the VI characteristics of a tungsten filament lamp. So there's that lamp that I keep talking about. And actually, let me go back for a sec. You see this little, like, I don't want to say wire, but this little filament here, this little piece of material, that's the tungsten. So the electricity, once it enters the light, it travels through one side, goes through the tungsten filament, comes back down here, and then exits to whatever other power source you have. Now, the tungsten filament, when the electricity flows through this material, it starts to heat up. And as the electrons encounter that resistance, it starts to release energy in other forms. So it converts the electrical energy that's going through the wires into light energy, and unfortunately, thermal energy. Most of you should probably know at this point that these bulbs are really inefficient. From 100% of the electricity that goes into powering them, 90% of it goes into producing heat, okay, and only 10% goes to producing light. Okay, so the compact fluorescents are much more efficient than that, which is why they are preferred. Okay, so here's the VI characteristics of the tungsten filament lamp. what is its power consumption at 0.5 milliamps and 1.5 milliamps? Well, we looked at the same graph before. We figured out the resistance at 0.5 milliamps and 1.5 milliamps. Now, in order to find the power, I mean, you can either use the resistance we calculated or you use the information directly from the graph, since I can find power using current times voltage. So just make sure when you plug in your current value, you're taking into account the milli prefix, so times 10 to the minus 3 times 0.08 volts. And we get 4 times 10 to the minus 5 watts. So watt is the unit for power. So if we look at this, actually I want to go back to this little box here for a moment. So we said power is work over time, or delta E over time. So work or change in energy, those are measured in joules, and time is measured in seconds, right? But we're being told that the unit for power is the watt. So that's spelled W-A-T-T. Okay, so things are measured in watts. Joule per second is a watt. How much energy per unit time? That's the power. That's how many watts. If you've ever changed a light bulb in your house, on the box of light bulbs, it'll say how many watts each bulb is. It might be 40 watts, it might be 60 watts, it might be something different. Okay. So we finally get into electric circuits. So things that we've been covering so far, I mean, that's been new material, but the things that we're going to be covering right now until the end of this video, all of this is review from grade 9 physics. Believe it or not, you would have already covered this based on the grade 9 science curriculum in the physics unit. You would have learned about series circuits, parallel circuits, and even something a bit more complex, the combination circuit of the two. We are still going to go over it here, but it is imperative that you know how to do this because, like I said, this is grade 9 material, which means we are going to get into stuff more complicated in the next video. Now, talking about electric circuits, there are a couple of important components for an electric circuit. There are the conductors, the components, and the voltage source. Every electric circuit needs a voltage source. That's going to be your battery or just some kind of power source. Right? Components, those are things in the circuit that actually are used. So that might be a motor, it might be a resistor, it might be a light, it might be a fan, something that gets turned on when the circuit is turned on, when the switch is closed. And conductors. So how does the electricity flow from the voltage source through the components? Using wires. Okay, so here's an example of a circuit. We've got 2 batteries here lined back to back, and we've got 3 resistors also lined back to back. In the one on the right, I've got 1 battery and I've got 3 resistors arranged parallel to one another. Now, in the case on the left, I have got the current traveling, well, counterclockwise. Now, if you're looking at that, some of you might be saying, okay, well, hang on, let me really think about that for a second. And on the diagram on the right, it's the same idea. We have arrows coming out of the plus side. I'm going to explain what all of this is by going to my sheet of paper. Okay, so first things first, let me just draw this diagram. So I've got 2 batteries. So here's plus and here's minus. The plus side always has that little point sticking out of it. And plus minus. Okay. Okay, so here's my circuit. I've got 3 resistors, I've got 2 batteries. Now, we know that electricity is flowing in the circuit, and we call that electricity current. Right? Current flows through the circuit. And what is current? Current means there are electrons flowing past a certain point in the circuit every certain amount of time. But electrons have a negative charge. Right? So if you have a negative charge, why would the negative charge leave the positive side of the battery and then head towards the negative side? If you remember the law of electric charges, based again from grade 9, you were taught that like charges repel and opposite charges attract. So this negative should be attracted to the positive and repelled from the negative. But for some reason, we draw the arrow for the current like this. So there's a very unfortunate reason for that. And well, it can't really be helped, but here it is. When scientists were first studying electricity, the structure of the atom was not well known at that point. Now we understand that in the nucleus, you have positive charges, which are the protons, you have neutral charges, which are the neutrons, and then orbiting around this nucleus, you have the electrons. So the electrons are free to move. They're easily able to move around the nucleus. However, whatever is in the nucleus is very, very tightly bound, and it cannot move. So these protons are stuck in there. But these electrons freely moving. This wasn't known at the time. So because they didn't know whether it was a positive or negative charge that was the charge carrier in the circuit, they said, you know what, let's just assume it's a positive charge. So if I was to stick a positive test charge, excuse me, if I was to stick a positive test charge somewhere in the circuit, where would it go? Well, the idea was if I stuck a positive charge here, it would get repelled from the positive terminal of the battery and it would be attracted toward the negative terminal. Hence, it would flow in this direction. Okay, so unfortunately, that system stuck. So even after the setup and the composition of the nucleus, the structure of the nucleus was discovered, it was already very late because many scientific papers and areas around the world already accepted this to be the direction of current. So this is a very confusing part, unfortunately, and it's something that we're stuck with. By definition, current is electrons moving through the circuit. This is also the definition for electricity, electrons moving through the circuit. If electrons don't move, that's called static electricity, right? That's when you rub the balloon on your hair and stick it to the wall. All right, so when we actually use this method, whenever we draw I, we draw it the direction a positive charge would move. And I, we label as conventional current. Now, sometimes this gets confusing because some books, in some cases, will start to draw current in the correct direction, and sometimes they draw it in the direction a positive charge would move. So I guess maybe it's better not to call this capital I, we'll just call it conventional current. Conventional meaning the old way, the original way. Conventional current is the direction a positive charge would flow through the circuit, and really that's all it is. Okay, so that's how we define the direction of I. It's the direction a positive charge would flow through the circuit, although we understand now that the positive charges, the protons, are tightly bound in the nucleus. They cannot just be moving through an electrical circuit. It is the electrons that move through, and that's what actually creates current. Okay, so going back to the slides. So unfortunately, that's why the arrows are going counterclockwise for the one on the left, and same thing here, the arrows are coming out of the positive terminal. Now, something to notice is that on the left I have what's called a single loop circuit, and on the right I have a triple loop circuit. Since it is the electrons that are moving, just go with it here, okay? Imagine the charge carriers are moving through, whether they're traveling clockwise or counterclockwise, they still have to go through all of the components of the electric circuit. The electrons in the case on the left, they all have to travel through the first resistor, through the second resistor, and then through the third resistor, then through the first battery, then through the second battery. And this cycle continues over and over again. So none of the electrons can skip any of these resistors or voltage sources. So when they move through the batteries, they gain voltage. And then when they go through the resistors, they dissipate or lose voltage. Okay, so then they come back here to the battery to regain voltage, kind of like someone spending money in a shopping mall. They go to the battery, they go to the bank, and they fill up money in their wallet. Then they go to store number 1, store number 2, and store number 3, and by the end of it all, they've spent all their money and they go back to the bank. Now, in the case on the right, electrons have 3 different paths to choose from. Now, based on how this is set up, you might think, well, the electrons would probably want to go through the first loop because it's the shortest distance from the battery. That's not exactly the case. Imagine you're trying to cross into the United States, or you're trying to go through any international border. Generally, you are waiting in a very long lineup. There are different toll booths that you can possibly pass through. So if you have ever taken the turnpike in a highway in the United States, these are tolled highways. But usually I like the example of the Canadian-US border better because there's always nice big lineups there, unless you show up there at 6 in the morning. So if you have 4 cars stopped at toll booth number 1, and you have 4 cars stopped at toll booth number 2, and you have 3 cars stopped at toll booth number 3, which one are you going to line up behind? You're going to line up behind toll booth number 3 because, well, that's just the most efficient way to get through. And assuming that all cars move through at the same pace, everything will balance out. So the same number of electrons will go to the first resistor, the second, and the third resistor. So they all experience the same voltage drop. Using the analogy of a person shopping at the mall, they go to the bank, they fill up their money. Okay, so in the case on the left, they go through 2 banks, so they get more money. Here, they go through 1 bank, so they get some money. Except we don't really have 1 person here. And in reality, even here, we didn't have 1 electron or 1 person. We have multiple people. So imagine you have 3 people here. Each person is going to go through 1 store, spend all their money at that 1 store, and then go back to the bank. Whereas in the case on the left, let's say you have 3 people. Each one of those 3 people has to go through each store and before they go back to the bank. Soldering joints. Okay, so if you have these resistors, how do you make the metals stick together? You have to heat them up to a very high temperature until they melt and they stick together and form a new cohesive bond. All right. Now, if you remember, we said any circuit will contain some voltage source, a component, and conductors. So here is the voltage source, the battery, and it's also known as a cell. This picture is in your data booklet. Now, if you have multiple cells attached back to back, that's what really we call a battery. Now, each one of these cells is rated at 1.5 volts. So if you stick 3 batteries or 3 cells back to back, that would be 1.5 plus 1.5 plus 1.5 volts, giving you 4.5 volts. Now, you can either draw it like this and have three of these cells back to back, which is not incorrect. That would represent 4.5 volts, as each one of these represents 1.5 volts. Or, and let me just go to the formula sheet for a moment, or you draw the battery like this. Because if you can imagine, if you have a 9-volt battery, you're going to be drawing a whole bunch of these back to back to back. So instead you draw 1 cell on the left, a line, and another cell on the right. It's not really necessary for you to do that. If you want to just draw a battery like this, it's fine. IB students have to be a little bit more careful. They have to actually draw it specifically like this. And non-IB, you can draw batteries and cells just like this. Okay. Now, I did say I'd come back to this page and explain to you which circuit symbols you have to be comfortable using and which ones you don't really need to worry about. Okay, so cell and battery, yes. AC supply you might see. Switch, that's for sure. Ammeter, that's for sure. Voltmeter, resistor, for sure. Variable resistor, potentiometer, lamp, and thermistor, you might. And light dependent resistor, you might. Okay, so just be ready for these ones. Lamp, for sure you're going to see, sorry. This for sure you're going to see. But variable resistor, potentiometer, thermistor, light dependent resistor, this L shape right here, maybe. Okay, so everything up here for sure, except this AC is also a maybe. This L shape here is a maybe. These 4 pieces down here, this is no. We are not covering those 4 at all. All right, back to here. All right, so like I said, each one of these is 1.5 volts. This is why when you see a battery, it's usually rated in increments of 1.5 volts. So either you have a 1.5 volt battery, you have a 4.5 volt battery, which is 3 cells in series, or you have a 9 volt battery. Okay, so any one of those combinations of 1.5 volts works. All right, now we're going to draw the schematic diagram and the circuit diagrams. So we have a series circuit on the left, series meaning the electricity only flows in one direction, In a parallel circuit here, the electrons can break up and move through different pathways. Okay, so for the one on the left, we've got our 3 resistors in series. We've got our cells, and since there's 2 of them, like I said, you can just draw one long line and one short line, or you can draw 2 back to back. That's fine. And for the case on the right, here are 3 resistors in parallel, and there's our single cell battery. Something to point out, this is not on the slides, but something you should write down, is that you see how the battery or the cell is represented with a long line and a short line? The long line corresponds to the positive terminal, and the short line corresponds to the negative terminal. Always remember that. Long line is positive, short line is negative. Okay, now these next couple slides, I'm just putting this stuff up fast, but you know what? I'm actually going to do the rest of today's video on paper because it's going to be a lot easier for you to see and understand what's going on by, well, seeing it on paper. All right. Now, let's say I have a series circuit. Okay, series means everything is in one line. And again, this is all grade 9 stuff, so I'm hoping that this is at least familiar to you. You got to have this stuff down cold. Okay. So we've got a cell. Now the cell is given this fancy letter, which we call epsilon. Epsilon is the name of this Greek letter, but the name that we give it is EMF. EMF stands for electromotive force. And the reason it's given such a name is originally when batteries were hooked up to these circuits, it was believed that the battery instills an actual force onto the electrons, which then pushes them through the circuit. We now know that there isn't an actual physical force acting on the electrons. The electrons simply move through the circuit as a result of there being a potential difference. Okay, now if that's not making a lot of sense to you, let me just give you a quick analogy. Let's say you take a balloon and you blow it up. Okay, so if you blow up a balloon and you tie the ends, think about the air pressure inside the balloon versus outside the balloon. Okay, you haven't tied it yet, but let's say you're just holding it closed with your fingers. Inside there is high air pressure and outside there is low air pressure, right? If there wasn't high pressure inside, well, you wouldn't have such a tense surface on the surface of the balloon. If you were to open this opening, but still hold your finger there to prevent the balloon from flying around, what happens? The air rushes out. So the air wants to go from a region of high pressure to low pressure. Most things in nature work like this. I say most because there are some exceptions, but for the most part, things move from regions of high pressure to low pressure. Air moves from high pressure to low pressure. Okay? Energy moves from high temperature to low temperature, always. Right? So in this case too, electrons or charges, they want to move from regions of high electric potential or high voltage to low voltage. All right. And so that's what actually causes the motion of charges through the circuit. It's not actually a force. This is just a name, once again, that was created long ago and just stuck. But anyways, we call that voltage of the battery epsilon. So this is the voltage of the battery. We're going to learn a lot about the battery voltage. In fact, that is what lesson 5.3 is all about. Now we have resistors. We have resistor 1, resistor 2, and resistor 3. What I want to do is try to derive, and let me go to the formula sheet here, try to derive these two formulas. I really hope these look familiar to you from grade 9 science, and if not, I mean, well, you're going to see it again now, so you're going to have to review this quite a bit. Okay, with a series circuit, okay, so remember I said the short side is negative, the long side is positive. I know the electrons are traveling out from the negative side. The electrons are traveling counterclockwise in this circuit. But because of because of unfortunate things that happened long ago, it was a 50-50 chance after all, we have to draw that the current is going like this. Okay, well that's fine. It's not a big deal. It still has to go through every single circuit element. So however many electrons there are here in this circuit, whether it's in the thousands or millions or billions or trillions, all of them have to travel through each of these. Okay, so every electron has to travel through resistor 1 before it gets to resistor 2 and before it gets to resistor 3 and then back to the battery. You just have to, right? So because this is a one-way street and you have to go through each of these toll booths one at a time. Now just imagine that for a moment. If you're stuck at the border and instead of having 3 toll booths side by side, you have 3 toll booths back to back. Each car has to go through each of those toll booths. So not only do you only have one path or one road, but each car has to stop 3 times. That's going to create a lot of resistance. And so when you have resistors in series, this creates a high resistance. And the more resistors you put in series, the more resistance there is. Just imagine, the more toll booths you put, the longer you're going to be stuck in your car trying to cross over the border or wherever you're trying to go. Now what we're going to try to do is come up with an expression for what's called the total resistance or the equivalent resistance. What that means is instead of having 3 tiny little resistors, what if I could just take those 3 and replace them with one single resistor? What resistance would it have to equal the individual resistances put together? Well, it's not always a matter of just adding them up. Sometimes it is, but sometimes it's not. It has to do with how the electrons behave in the circuit. So I know I have 3 different resistances, R1, R2, and R3. Now, I know I have a total voltage for the circuit, so we can call that VT or epsilon. Okay, so there's a total voltage, but, so actually let's put that up here, VT, and there's a total resistance. We have a total voltage. Now, remember, treat the battery like a bank. You go to the bank, you fill up money, then you go through store number 1 or you go through toll booth number 1 and you give them some money. Then you go through toll booth number 2, you give them some money. You go through toll booth number 3 and you give the rest of your money. And then you come back to the bank and fill up your money. So by the time you go through resistor 3, you shouldn't have any money left. So how does that correspond to the electrical analogy? That means in resistor 1, you have some kind of a voltage drop, V1. In resistor 2, you have some kind of voltage drop, V2. And in resistor 3, you have some kind of voltage drop, V3. Now, at the source, at the battery, you gain voltage. So V total is equal to V1 plus V2 plus V3. That's important. So for a series circuit, VT equals V1 plus V2 plus V3. Now, using Ohm's law, V is equal to IR. I know that the current going through this, whatever current goes through the battery, however many electrons per unit time go through the battery, it's the same electrons per unit time that go through the first resistor, the second resistor, and the third resistor, because, well, they're all back to back. Okay? So the currents are all the same. That's really important. So I1 equals I2 equals I3 equals I total, because there's only one path for the electrons to go, so it's got to be the same. All right, so using these 2 pieces of information with V is equal to IR, I can now rewrite it like this. V total is equal to I total times R total. And V1 is I1 times R1. V2 is I2 times R2. And V3 is I3 times R3. Now, the very fact that all of the currents are the same, that means I have the same value in each of these terms. I can cancel them out because they appear in every single term, leaving the ones behind. And so, what do we end up with? We end up with total resistance is equal to R1 plus R2 plus R3. And if you have more resistances in series, it becomes all the way to plus Rn, however many you have. So this is the expression for the total resistance in a series circuit. And if you look at your formula booklet, that's right here. R total equals R1 plus R2 plus ... It does not tell you here that this is for a series. You have to understand that yourself. Okay, so just to summarize, we came up with this expression by concluding that the total voltage in a series circuit is the sum of all the individual voltages. So this is what you get from the battery. This is what you dissipate at each one of the resistors. The current in a series circuit is the same, whether it's from the battery, it's going through resistor 1, 2, 3, whichever one it's going through. Okay. So that is for series. Now let's talk about parallel. All right, in a parallel circuit, so let's say we have our battery. So we have toll booth number 1, toll booth number 2, and toll booth number 3. So R1, R2, and R3. Here's epsilon. There's my negative and positive sides. You don't have to label that, by the way, every time. I mean, at a certain point, you're just going to remember that this is negative, that's positive, so you won't need to write it. If we sketch in our conventional current, which is the direction a positive charge would want to move if it was placed in the circuit, the conventional current would look like this. Well, we would have the current coming out of the positive side. Now, once it gets to this junction, right, so actually let me just make sure it's solidly drawn in. Once it gets to the junction, some of it's going to come here and some of it will continue, right? So if these are cars driving and they have to go through a toll booth, 1/3 of them will branch off here and the other 2/3 will continue. Okay, once they get to the next junction, 1/3 will come here and the other 1/3 continues on. Okay, so finally this 1/3 combines with this 1/3 to give you 2/3 at this junction. So now we have 2/3 traveling to the left. This 2/3 combines with the original 1/3, giving you 3/3 or 1 whole, and they go back to the battery. So this is how the current travels in a parallel circuit. So what that means is if you call the current going through R1, I1, and you call the current going through R2, I2, and the current going through R3, I3, and the current going through the battery, I total, I can see that only part of it goes through I1, part of it goes through I2, part of it goes through I3. And let me just be very clear. The reason why 1/3, 1/3, 1/3, like it splits exactly evenly, is because each of these resistors has the same resistance value. Imagine the resistance as the pace that the worker works. If you have a really slow worker sitting right here, imagine the resistance of this piece right here, this instrument, is very high. If this person's working really slow, less people are going to line up here. So more people would line up at R1 and R3. Okay, less people here, which means the current through I1 and I3 would be higher. The current through I2 would be lower. But for now, we're just going to assume they're all the same resistance. But regardless, this formula will still hold even if they're not. And that is that the total current that goes through the battery is equal to the sum of I1 plus I2 plus I3. Regardless of how it's split up, whether it's even or not, this will always be true. Now, because each of these is in parallel with the battery, each of these has the same voltage drop. This is another property of parallel circuits. V total equals V1 equals V2 equals V3. And the reason for that, imagine the battery is the bank. Okay, so some people will go through toll booth 1, some people will go through toll booth 2, some people will go through toll booth 3. You're not going to go through toll booths 1, 2, and 3. You just go through one and then you come back to the bank. So however much money or voltage you gain here, you deposit all of it in the parallel resistor. So that's why the voltage here, here, and here all have to match that coming from the battery. Now, using this first expression of current, so IT is equal to I1 plus I2 plus I3, using that combined with Ohm's law is V is equal to I times R, or I is equal to V divided by R. I'm going to now replace this with expressions of V and R. So I total is V total divided by R total. I1 is V1 over R1, I2 is V2 over R2, and I3 is V3 over R3. And of course, this can continue if you have more pieces to the puzzle. Now, since all the voltages are the same, due to the fact that all the resistors are in parallel with the battery, all of these appear in each term. So I cancel it out, leaving a 1 in each place. So I'm left with 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. So this is how to calculate the total resistance when the resistors are connected in parallel. Notice that the total resistance is underneath the 1. So once you calculate the right side of this formula, then you have to take the reciprocal of that to get our total. We'll do an example of that, and then that will be the end of this video. So everything that I've just talked about is here. Let's do a first example, and this first example is on the series circuit. Then we'll have one example on the parallel circuit, and then we're done. Okay, Three resistors of 330 ohms each are connected to a 6-volt battery in series as shown. What is the circuit's equivalent resistance? Okay, so equivalent resistance is the same thing as total resistance. So let me just quickly sketch this. I'm going to switch screens now. Okay, so everything is in series here. And by the way, let me just show you guys the formula booklet. You probably saw here, there's the expression for total resistance in a parallel circuit. Again, it's not labeled as such. You have to understand that that's what it's for. Okay, so we are looking for equivalent resistance. So R total. Some people call it R sub EQ, up to you. This is epsilon. Now epsilon, we're told, is 6 volts. And each of these resistors, so R1 equals R2 equals R3, which is 330 ohms. Due to the fact that it's a resistor, sorry, it's a circuit where all the resistors are connected in series, I know that the total resistance is equal to R1 plus R2 plus R3. So what is that? So that's 330 ohms plus 330 ohms plus 330 ohms. That's 990 ohms. So what that means is, technically, instead of having R1, R2, and R3, this circuit is equivalent to this one right here, having only one resistor, if its resistance was 990 ohms. Those two would operate exactly the same. Okay, back to the slides. Oh, what is the current in the circuit? My apologies, I didn't do that. Okay, so we just did part A. What is the current in the circuit? Well, if we want to draw the direction of conventional current, remember that the short side is minus, the long side is plus. So unfortunately, that's the direction of conventional current. It's the same current that goes through the battery through R1, R2, and R3. And so really you can just use the total values. I know total voltage, that's called epsilon, and it's 6 volts. I now know, and this is part B by the way, I now know the total resistance, it's 990 ohms, and I can find the total current because that is the same thing as I1, I2, etc., which is what we're looking for. So using Ohm's law, V is equal to I times R. I is equal to V divided by R, so that's I total equals V total over R total. That's 6 volts divided by 990 ohms. Both are SI units, so I can go ahead and just plug it in my calculator. So that's I total is equal to 6.06 times 10 to the minus 3 amps, also known as 6.1 milliamperes. Okay. What is the voltage on each resistor? Okay, so still on this question, part C, what is the voltage on each resistor? Well, remember that for a series circuit, the voltage, you gain the voltage at the battery, and then you dissipate some of the voltage in R1, some in R2, some in R3. And the analogy was, if the toll booth operator is really slow at one of them, that means there's going to be, well, more time spent here, right? So all of these resistors are rated the same. They're all 330 ohms, so they're all identical, meaning that the voltage drop across each of these has to be the same. So since R1 equals R2 equals R3, therefore V1 equals V2 equals V3. These two are going to be the same. So my 6 volts divided evenly amongst each of those three, that's going to be 2 volts, 2 volts, 2 volts. Now that's not the only way to figure it out. I mean, we can confirm our value by simply calculating the current for any one of them. Okay, so for instance, if I wanted to find I1 using Ohm's law, it's going to be V1 over R1. So therefore, V1 equals I1 times R1. I know that I1 is the same thing as this. So 6.1 times 10 to the minus 3. What's the resistance? It's 330 ohms. So if we do that, 6.1 times 10 to the minus 3 times 330, we get 2.013. Okay, so that's approximately 2 volts. So same answer. Okay, and there's the answer to part C. So whether you're looking at that or you're looking at that. All right. And finally, our example in parallel. So this is the conceptual part, which we've already gone through. Okay, and finally, the example. 3 resistors of 330 ohms each are connected to a 6-volt cell in parallel as shown. What is the circuit's resistance and what is the voltage on each resistor? Okay, so here we go. So we have 3 of these in parallel. By the way, I know I keep saying this, but it's just important for you to understand. This is all grade 9 material, by the way. So everything that we're doing right now has already been covered in grade 9 science. So you got to have this stuff down cold. R1, R2, R3, epsilon. I think the only difference would be you probably didn't call this epsilon. You probably just called it V total. All right, so each of these resistors has the same resistance, and that's 330 ohms. The voltage of the cell, epsilon, which we're just going to call VT, is 6 volts. What is the circuit's resistance? So that means I'm looking for the total equivalent resistance. Well, when dealing with a parallel circuit, I know that 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? Or however many more I have. So they're all the same. So that's 1 over 330 plus 1 over 330 plus 1 over 330. Or you could just do 3 times 1 over 330. In fact, I will. So all of these have the same denominator. So it's 1 plus 1 plus 1 in the numerator, which is 3. Now, this is where so many students are going to make a mistake. And despite me saying this, there will still be some of you, unfortunately, that fall into this trap. Some of you are going to say 3 divided by 330 equals this number right here. That's our total, because you will forget to include the left side of this in the formula in the solution. So therefore, the resistance is 9.1 times 10 to the minus 3. I mean, that's pretty low, and you would certainly expect a lower overall resistance when the resistors are in parallel compared to series, but I mean, you're going from 990 to almost 0. Okay, so that's not correct. You have to remember that the left side of this formula is equal to 1 over R total. So this, whatever you get here, is 1 over R total. So whatever number you get, you have to take 1 and divide it by that number to get the answer, 110. Another way to see it is the way I've done it here. Sometimes the numbers work out nice with the fractions, like it does here. 1 over R total is 3 over 330, which means R total over 1, so flip each of the fractions, is 330 divided by 3. That's 110 ohms. So what that means is that this circuit could be replaced. So take out those 3 resistors and replace it with a single resistor of 110 ohms. That's the same thing as having 3 of these side by side. So that's part A. What is the circuit's resistance? Part B, what is the voltage on each resistor? So if you remember with a parallel circuit, whatever voltage you have for the source, it's the same voltage across each of these. Now, that's assuming that the resistance is the same, which it is. Okay, so I know that each of the voltages, so for part B, I know that V1 equals V2 equals V3 equals V total, since all in parallel. And so they all equal 6 volts. Okay, now let's go to the slides. Part C, what is the current in each resistor? Okay, last part. Part C. So I'm looking for I1, I2, and I3. Okay. Since it's the same resistor, we know that the current, whatever the total current is, it's going to get split evenly. So this is plus, this is minus. So part of the current goes here, part goes here, and part goes here. And then they merge again and go back to the battery. So Again, in this case, I know that the currents are going to be the same. So this here would be I3, this would be I2, this would be I1, and only because the resistances are the same. If they weren't, then I would calculate it one by one. So for example, if they weren't the same, I would say, okay, well, V equals I times R. So I is equal to V divided by R. So that's, if I want to know I1, it would be V1 over R1. And I know that the voltage across all of them is the same. It's 6 volts. And if I divided that by R1, which is 330 ohms, I'm going to get my current. 6 divided by 330, 0.018. And that's going to be amperes. Or this could be 18 milliamperes. Actually, I don't need that squiggly line there. Okay, so that's one way I could do it, and I could do that for each of them. Or I could just recognize that in this case, they all happen to be the same, right? Because all the resistances are the same. And so all the currents are going to be the same. And I would find it out like this. I total is equal to V total over R total. So V total is also 6 volts. R total is 110 ohms. 6 divided by, oh, hang on. Let me just think about this 1 second here. Yeah, okay, so 6 is equal to, or 6 divided by 110. So I get 0.054. 0.0545, and this continues. So this would be the total current going through the battery, 0.0545. And if you take that and you divide it 3 ways, you get 0.018 amperes. But there is your answer. So you find it individually, which is technically always going to work for you, or you figure it out based on logic, which also works. Okay, so that is the end of this video, part 1 of 2 for 5.2 heating effect of electric currents. Stay tuned for video 2 of 2 for 5.2.